Good morning, ladies. This beautiful, dreary day that we're having in Evansville. So life is good. So let's start off with a couple reminders and announcements. So reminder is exam 4 is 1 week from tomorrow because it's summertime and it's relentless and we always have to have exams like every day. And then the second announcement is, announcement, I should say. Chapters 20 and 21, which we're going to start today. Those homeworks are already posted. Actually, I think 20 is already posted and 21 will show up tonight, but that's okay. We're only going to start chapter 20 tonight. So those are the two chapters that we're going to go through for this next exam. And then we have all of next week and then a week after that, and basically we're done. So we have 2 weeks and 2 days. That's all we have left. So,
is homework still not mandatory?
Homework is still not mandatory. Yeah. So it's still there just for extra practice, but yeah, still not mandatory.
Okay, just making sure.
All right. So today we're going to start chapter 20, which will be our first chapter into the next section of the class, which deals entirely with magnetism. So far we've seen all electrical effects. So now we're going to start our chapter 20, which is into now magnetism. So now we're going to start looking at magnetism. So first thing we're going to do is actually compare and contrast electricity and magnetism together. So let's talk about electricity and magnetism. Okay. So typically magnetism or magnetic fields we're going to call B. So B here with a vector sign is equal then to the magnetic field. So it turns out that magnetic fields are very similar to electric fields in the fact that they are both fields and they both are created by certain objects. So let's talk about first what creates an electric field. So let's talk about what creates the field. Well, we know that, based off our conversations before, what actually creates an electric field is charge. And so if we have positive charges, negative charges, we know those things create electric fields. So in this case, we know that this is actually charge, actually, which creates an electric field. There's more things, but I'm going to leave it there. What creates a magnetic field is actually moving charges, i.e. currents. So currents are actually the source of magnetic fields, and we'll talk more about that. Now, what's kind of interesting about magnetic fields is, again, if you go back to charge, what we know is that charge, there are two flavors of charges. Right? So we have two flavors. We have a positive charge and a negative charge. And these are what we call monopoles. Right? So these are monopoles, which basically means that if we were looking around, we could have a positive charge basically all by itself, or we could have a negative charge all by itself, and each one of those would create their own field. But it turns out that in magnetism, we don't have monopoles. So one of the fundamental ideas then of magnetism is that we can never actually find a magnetic monopole. So one of the ideas here is that magnetic monopoles do not exist because we've never actually seen one. So magnetic monopoles don't exist. So what does that mean? So that means that we could never, ever, ever find something. Somebody just tried to show up. Okay, maybe I was just freaking out. Okay. Oh yeah, there we go. Oh, we lost hair. Gotcha. So what this means is that if we thought about something that creates a magnetic field, something like a bar magnet, which is a little more complicated to talk about, but let's talk about a bar magnet. So if we're talking about a bar magnet, for example, we know that it comes as both. So this is actually a magnetic dipole in the fact that there's a north side and a south side. So we have magnetic field lines which are going to go around and do something like this. Well, what happens if I take that bar magnet and I cut it? So for example, if I take this guy and I cut it in half, Well, in this case, now I'm going to make two smaller bar magnets, one north side, one south side. Over here, I'm going to make a north side and a south side. And then if I took this one and I cut it, I'm now going to make, again, two smaller bar magnets, still with a north side and a south side, and a north side with a south side, which means if we keep cutting the bar magnets, we can never get to the point where we have just a single north pole by itself, or a south pole by itself. So that's what this thing says. So we have never ever witnessed in nature something which is called a magnetic monopole. So this is actually one of the most interesting ideas kind of in magnetism, is that these magnetic monopoles don't actually exist, which is actually kind of funny because in a lot of our fundamental theories of physics, monopoles are consequences of a lot of things that we find. So for example, if you talk about what happened kind of before the Big Bang, what happened then going from the Big Bang to what we have now, you have what's called the symmetry breaking, where you would then create relics of the original symmetry. And the idea, or at least the math tells us that what we should create is actually magnetic monopoles. So what we should have actually throughout our entire universe is actually magnetic monopoles, due to the fact that we went from something which had a higher symmetry to a lower symmetry after the Big Bang, which means that our universe should actually be encompassed by magnetic monopoles. But since we've never actually found one in nature, we had to go through extremes to basically get rid of these magnetic monopoles that our theory actually predicts. So this is where the idea of inflation came from. So if any of you know what inflation is after the Big Bang, our universe went over this period of very highly rapid expansion, which then caused our universe to basically, maybe increase from the size of a pea all the way up to almost what we see today. So rapid expansion. So this is what we call inflation. Now, where does magnetic monopoles come from that? Well, the idea was, and this was put forth by Alan Guth, who is a physicist at MIT, if I remember correctly. So anyways, his idea was that since we have these magnetic monopoles that should not exist due to the fact that we now have the symmetry breaking, well, what happens if we take our universe and we expand the crap out of it? So we make it so big, what happens to all those magnetic monopoles? Well, basically, we still have the same number of magnetic monopoles, but the difference is if I had 100 magnetic monopoles in a size that's this big versus 100, which is in the size of this big, the odds of finding one is now relatively small, right? So basically, going through and introducing this idea of inflation, which ended up solving all kinds of other problems, but actually was nothing more than to hide these magnetic monopoles by saying that, okay, now if I take the size of my universe and I make it huge, the probability of actually finding one of these magnetic monopoles basically goes to zero. So, sure, nobody actually cared about that, but I like talking about it. It's fun. So anyways, that's where this idea of inflation comes from. So basically, just to do what you do when you're a child and you make a mess, instead of picking it up, you hide it under the rug because it's a lot easier to do that as opposed to actually dealing with the consequence of that. So great. So anyways, having said all that, so again, we know what creates then the electric field is charge. So here we have monopoles. We have single charges which create electric fields. For magnetism, we have to have moving charges, i.e. currents, and these never exist as a single pole by itself. Good, so let's talk about the type of force. So here, the type of force that we have with electric field is this is a long distance force. For magnetism, this is also long distance force. So you can move two magnets somewhere near each other and actually create a force between them without actually touching those. Let's see, let's talk about the interaction. So the force interaction. There we go. So here what we know is that what? Like charges equal repulsive force, and unlike charges equals then a attractive force. For magnetism, it's actually the same. So here, if we have like poles, then that equals a repulsive force. Where if we have unlike poles, then this equals an attractive force. So it just means that what if I had two bar magnets where this was the north side and this was also the north side, here I'm going to get a repulsive force. So the two of them are also going to feel. So this one's going to feel a force in this direction, and this one would feel a force in this direction. Good, so let's talk about the field lines. So what do the field lines look like for these guys? Well, we know for electric fields, the field lines always go in straight lines, right? So again, if I had my positive charge here and I drew my electric field lines that go away from that, then these are starting at the positive and they resonate away. So these actually have a beginning, where for negative charge, this acts as the sink. So this would be the end of the field lines. So these go in straight lines. With a beginning and an end. Or an end, I should probably say. If I had just a single charge, there's only a beginning or an end. It's a beginning or an end. For magnetic fields, these are actually always going to form closed loops. Hence, there is no beginning or no end. No beginning and no end. So anytime I have a magnetic field, such as we drew here, so for example, again, if I look at a bar magnet, so again, let's say this is the north side, this is the south side, then magnetic field lines would come out, go through, wrap around, go through the bar magnet itself, and then create a closed loop. This side, it would do the same thing. So come through and then go back in and then create these closed loops. So these are always going to be closed loops, something circular in nature. Again, no beginning and no end. These ones are straight lines unless there's other charges, which we'll cause them to bend. Detection of the field lines. So we know that, going back to what we did before, that the way we would detect electric field lines is we use a positive test charge. Then direction of the force is in the direction of the electric field. Direction of F is in direction of E. So the electric field points in exactly the same direction as the force because we're dealing with positive test charges. For magnetic fields, it's actually very similar, but here, instead of using a simple charge, since we have no simple charges, we only have dipoles, we're going to use then a bar magnet or a compass. So here we take a compass, place into a B field, then direction of North Pole is direction of the field. So for example, if this was my system I'm trying to find a magnetic field from here, I would then simply put a compass here. And then at this point, the direction of the compass needle, which would point along the direction of the North Pole, then would be the direction of the magnetic field. So this would be my magnetic field here. Or if I put a magnet or a compass here, so at this point, again, my magnetic field would point in the direction at which the North Pole would be pointing. So that would point in this direction. So this would be the direction of the magnetic field. So that means that if we thought about the Earth, right? So let's say here's the Earth, and I had my compass here at the Earth, and my compass is pointing in this direction, telling me that north is pointing this way. That means that the magnetic field line of the Earth is pointing in this direction, which means this is the direction of the magnetic field. But this would be then the magnetic South Pole, because the north would be pointing towards the south because it's attracted to the south. And this would be the magnetic North Pole because it would be pointing away then from the North Pole. Right? So actually, the way that it works on the Earth is what we call the North Pole is actually the magnetic South Pole. And what we call the South Pole is actually the magnetic North Pole. So the North Pole of the Earth is actually equal to the magnetic South Pole of the Earth. And these two are actually slightly different from each other. There's like a 5 or 10 degrees difference between the actual geometric north versus the magnetic north. So these things are actually slightly different from each other. But yeah, so just remember, whenever you're driving north, you're actually driving towards the magnetic South Pole, not in the north direction. So technically you're going south, but that's okay. Not to confuse everybody. We'll be fine. Okay. So these are kind of contrasting the two. So again, what creates an electric field are charges. So electric monopoles. What creates magnetic fields are currents. The force on both of them are both long-range forces. The interactions of the forces are basically the same. So again, like repel each other, unlike attract each other. For field lines, again, the electric field lines are always circular in nature, straight in nature, where the magnetic field are actually circular in nature. And the detection, again, is done the same way, where you would place some sort of object, where for the electric field, you put a positive charge in there, measure the force and its direction, that tells you the direction of the electric field, where for the magnetic field, it's done with the compass. So again, you would measure the torque in this case, as opposed to the force, which would then tell you the magnitude of that field. Okay. So basically, unfortunately, we don't give the magnetic field as much love as we should, because we basically say, okay, it's pretty much the same thing as the electric field, so let's move on. It's a little more complicated than that, and there's some other things that we'll kind of point out along the way, but that's about as much as we're really going to spend talking about that type of thing. Okay. The other thing to kind of pay attention to is that the magnetic field is always perpendicular to the electric field. So those two are always perpendicular to each other. So good. So let's talk about direction of magnetic fields. So let's talk about direction of magnetic fields. In a current carrying wire. So let's say we have a wire where this wire then is going to carry current, and we want to know what is the direction of the magnetic field based off of the direction at which this current is running. Okay, so this is what we want to know. So let's say we have current running in this direction. We want to know what is then the direction of the magnetic field. So let me show you a quick video so you can kind of see that. So here, there is a wire. So this is the wire kind of running in this direction. Let me make that a little bit bigger. There we go. So here's the wire, and it's going to extend down through the opposite side here. And then here I have compasses. I shouldn't say I have, but they have compasses, where they're all pointing in the North Pole, which is in this direction here. Okay. So right now the current is turned off. And then what they're going to do is they're going to turn on the current, and we want to watch what happens to these compass needles. Now remember, the direction of the North Pole, or the north side of that compass needle, points in the direction of the magnetic field. So now they turn on the current. And what you see now is that the north on this one is slightly shifted. North on this one has gone to the west direction. The north on this one has basically gone, almost towards the south direction. On this one, it's gone east. And again, this one, it points relatively in the same direction. So basically, again, let me back it up just a second. So again, initially, these guys are all pointing in the same direction. But as soon as that current is turned on, each one of those compass needles then feels a torque, which then point in the direction of the local magnetic field. So again, for him, local magnetic field now points this way. For him, points this way. For him, it kind of points this way. And for him, it points this way. So if I think about drawing all of these guys basically on top of each other, again, what we can see is that this is creating a closed loop, where that closed loop points in a particular direction. That particular direction is the direction of the magnetic field, which is given by what's known as the right-hand rule. So the right-hand rule tells us the direction at which the magnetic field is curling around based off of what these compass needles are basically doing. So that brings us back to our picture here. So here, again, if I have current running through my wire, what's going to happen then is the direction of the magnetic field curling around this wire is actually going to go around in this direction. So it's going to be the direction of the magnetic field, which again, we would see from that particular example there, where this one is now pointing in this direction, this one was pointing this way, and this one was pointing this way, this one was pointing this way. Okay. So this is what we call the right-hand rule. So let's call this right-hand rule number 1. So the right-hand rule number 1 says is for determining the direction of the magnetic field from a current carrying wire, we first, number 1, point thumb of the right hand. So of right hand in direction of the currents. So in the direction of I. Now remember, I is not a vector, but we're going to pretend it's a vector and say it's flowing in a particular direction. Step number 2, curl fingers in direction of the magnetic field. Okay. So first off, this is called the right-hand rule for a reason, which means which hand do you use?
The right one.
The right one, good. Even though what'll end up happening to you, especially if you were actually in class taking the exam, for those of us who are right-handed, such as myself, when you're trying to figure out the direction, it's a lot easier to use your left hand because you don't have to actually put down the pencil or the pen when you're actually doing the exam or doing your homework or doing whatever. But this will give you the wrong direction. So it's called the right-hand rule because we use our right hand. Okay. So again, the way that this works is what you do is you imagine that you're grabbing the wire. So here, my wire is pointing this way, right? So let's pretend this is my wire. Current is running in this direction, which is in the direction of the tip. So you pretend that you're grabbing the wire with your thumb pointing in the direction of the current, and then your fingers wrap around in the direction of the magnetic field. Okay. So this is the way that the right-hand rule works. So you grab the wire with your thumb pointing in the direction of the current, your fingers then curl around in the direction of the magnetic field, which is exactly what we drew here. Right? So this is what we call right-hand rule number 1. So let's do a couple more examples. So let's say, here's my wire. It's going to be pointing in this direction. So it's perpendicular to the page. And let's say I have current running out to the page. So anytime I draw a dot with a circle around it, this equals out or toward you. So in this case, out of the page or toward you. As opposed to if I drew the wire and instead put an X into it, so this would be equal to in or away from you. So if you want to think about these as an arrow, so in this case, you see the tip of the arrow coming directly at you. In this case, you're seeing the quiver where you're seeing the feathers moving away from you. So here, so again, if we want to know the direction of the magnetic field, again, we would grab the wire, put our thumb in the direction of the current. So for example, the bottom one down here. So for use my laser pointer. So for this one here, I would grab the wire with my thumb pointing towards me, and then my fingers would wrap around in the direction of the magnetic field, which means if I was looking at it, what I would see then is that the current would be, or the magnetic field would be going around in the counterclockwise direction. So this would give me a counterclockwise magnetic field. As opposed to when it's doing the opposite, that I put my thumb pointing away from me, I would grab the wire. In that case, my thumb would curl, or my fingers would curl around then in the clockwise direction. So in this case, my magnetic field would go around in this direction, which would be the clockwise direction. So this is what we call right-hand rule number 1. So right-hand rule number 1 works for now only for a wire which is carrying currents. Okay. So, good. So now what we want to know is, now that we know that's what, this guy is going to create his own magnetic field, where that magnetic field is going to be perpendicular to the current. Right? So here I have current running in this direction, or here I have current running in this direction, and the magnetic field is in a perpendicular plane according to that. So here we know that B is perpendicular to the current. Okay. Great. So now that we know that this guy creates a magnetic field and we know what that magnetic field looks like, we'll talk about the magnitude of that field in a while. We now want to know is if I took that same wire and I put that into an external magnetic field, what's going to happen to it? So let's say that here's my wire, and I'm going to put this guy in some external magnetic field. So let's say that's what? Let's call this my external magnetic field, pointing in this direction. So this is B external. And let's say I run current through this wire. Let's say my current is running in this direction. What's then going to happen to the wire? Okay. Well, again, here what's going to happen is I have an external magnetic field. My wire is going to be carrying current, which means my wire is going to be creating its own magnetic field. So in this case, again, I put my thumb in the direction of the current, run my fingers around the wire. So in this case, my magnetic field for my wire is going to be running around like this. So it's going to be B of the wire. These two then are going to create an interaction between them, which is actually going to generate a force. Okay. So what's going to happen then is if I take this wire and I put it into this external magnetic field, this is now going to create a force. And we want to know, what does the force on this guy look like? Now, to do that, I'm going to show you, stop sharing, and I'm going to show you this beautiful setup that I have back here. This is going to basically show all this for us, hopefully. So, can you guys still hear me if I stand way back here?
Yeah.
Okay, good. So what this is what's called the cathode ray tube. So basically what I have here are, so this is a amplifier, which basically is going to take potential from here, amplify it to put a huge potential difference across here. Now inside of here is a gas, so when I put a huge potential difference across here, what's going to happen is I'm going to strip off electrons inside of this gas, and then I'm basically going to create an electron beam, which is going to move in one direction. Okay. Now that electron beam is going to basically act as if it is our current carrying wire. Right? Because remember, charges which are moving constitutes a current. So let me turn this guy on. I want to be stable. There we go. Okay. So this is my current carrying wire, right? It's moving in this direction. So what happens if I take this magnet here? So this is a neodymium magnet. So this is a very powerful magnet. And if I put it near the field, I can actually cause this thing to move and bend, do all kinds of different stuff depending on how I actually move and move. Which means I'm actually applying a force then to these charged particles, i.e. to the wire, to cause it to bend in different directions. Now, can you guys see that? I don't know how well this is actually showing up. Yeah. Good. So again, I can get it to bend down, or get it to bend up, or have it move around in different directions, depending on this wire. Okay. So this is basically what we're looking at. So we're saying is that we have a current, again, running through here. Let me turn it back on. Okay, that's going to basically be our wire as this thing is moving through. And as I put the magnet near it, I can actually cause the beam to bend, which would act as if I'm putting this force then onto the wire, due to putting it in next to an external magnetic field. So what we want to know then is, what does the force on this thing actually look like? So let's say that we're going to, again, take this magnetic field, we're going to put it into then, put the wire into this external magnetic field, and we're going to do a whole bunch of different experiments. So let's say experiment number one is, we're going to have, that's what? The magnetic field is, say, parallel to the current. Okay? So in this case, we're going to have this external magnetic field being parallel to the current. Number two, we're going to say that the external magnetic field is perpendicular to the current. Number three, we're going to switch the direction of the current and see what happens. So meaning instead of having the current go in this direction, we're going to flop it so it's going to actually move in this direction. Okay. Number 4, we're then going to what? Increase the strength of the magnetic field when it's perpendicular to the current and see what happens. And then number 5, we're going to take the length of the wire here. So let's say this is the length of our wire. And we're going to increase the length of the wire with the magnetic field being perpendicular to the current. Okay. So here we're going to increase the external magnetic field. And then finally, the last thing we're going to do for number 6 is we're going to increase the current when, again, the external magnetic field is perpendicular to that current, just to make it a little bit easier, okay? So basically, these are the 6 experiments that we're going to look at, okay? And we're going to see what actually happens. Now, I'm not going to do them here. We're just going to discuss them and talk about the results of them. So let's talk about the results of these. Experiment number 1, what we find in this case is if the external magnetic field is parallel to the current. So in this case, if here was my wire, where my current is pointing in this direction, and then my external magnetic field was, say, pointing in this direction, so this was B external, we find in this case then is the result of this is that there is no force. The force on the wire is equal to 0. Okay. Experiment number 2. Now, we're going to take that same situation, but now I'm going to put the external magnetic field so that is perpendicular to the wire. And then here, what we find is that the result of this is that the force is not 0, and in fact, the force is equal to a maximum. So this is the maximum amount of force that we can get. Experiment number 3, we're now going to change the direction of the current, which means that we're going to actually switch the direction of this magnetic field to the opposite direction. The result of this experiment is that the direction of the force, so we're going to call that F3, is actually equal to minus of F2. So what happens is that what? The direction of the force actually switches, rotates by 180 degrees, and it's still equal to its maximum. So it's still equal to minus F max. Number 4, what happens if we increase the external magnetic field? Well, in this case, what we find is that as the magnetic field externally increases, at least the magnitude increases, then the magnitude of the force also increases. So the force on the wire gets bigger. Number 5. Number 5 is if we take the length of the wire and we increase the length of the wire, meaning we put more of the wire inside of this external magnetic field, what happens in this case is what we find is if the length of the wire increases, the magnitude of the force also increases. So more force is on the wire. And finally, number 6, if we increase the size of the current, i.e. make the magnetic field of the wire bigger, what happens in this case then is that also the force increases. So the magnitude of the force, again, increases. Okay. So let's talk about what each one of these actually implies to us then. So let's start off now with number 4. So number 4 implies to us that what? The magnitude of the force on the wire then has to be proportional then to the external magnetic field. I'm simply going to call that B. Because if I increase the size of the magnetic field, I'm also increasing the size of the force. Number 5 implies the same thing. So if this tells me that the magnitude of the magnetic field is also then directly proportional to the length of the wire. The next one then tells me that what? If I increase the current inside of the wire, the magnetic or the force increases, and that tells me again that the magnitude of the force is also directly proportional to the current in the wire. These two together, 1 and 2, imply to me that what? There's an angle dependence, and that angle dependence is a sine. Because what? When the magnetic field is parallel to the direction of the currents, we have 0, and we know sine of 0 is simply equal to 0. But when there's a 90-degree separation between the two, in that case, we know sine of 90 is equal to 1, which is its maximum value. Okay. So taking these things and putting them all together, and we'll talk about what the third one implies to us here in a second. What this tells us then is that the force on a current carrying wire is then equal to I times L times B times sine of the angle between the two. So this tells us that the magnitude of the force on this current carrying wire is equal to the current of the wire times the length of the wire times the magnitude of the external magnetic field times sine of the angle between the two. So this angle here is the angle between the L, technically, but we'll write it as the current. So if this is the direction of the current, this is then the direction of the external magnetic field. Then the angle here is the angle specifically between those two. Now, again, typically what happens is since the current is a scalar quantity, what we end up actually doing is we apply the vector portion to the length. So what we're usually going to do is here is my wire, and I have current, say, running again in this direction. Then what we usually do is we assign a vector to this, which is the length vector, L vector, which is a vector which points in the direction of the current. So this is L vector, whose magnitude then is equal to the length of the wire. So the magnitude of this vector L is then equal to the length of the wire, where this is the length of the wire. Again, that's basically just the way that we have defined the current. We have defined the current as not a vector, so we have to put a vector sign on something, which we're going to call the length vector here. So what does number 3 imply to us? Number 3 implies to us that since this thing changes, if I change the direction of the current, this implies to us that in vector form, this is what's known as a cross product. So the force on a current carrying wire then is going to be the current times L crossed by B. Okay, so this is actually the force on a current carrying wire. This is IL cross B. Okay. This brings us to the next right-hand rule. So let's talk about right-hand rule number 2. So right-hand rule number 2. So what does right-hand rule number 2 say? So right-hand rule number 2 says if I have something that says A cross B is equal to C, then the way this works is step number 1. Point fingers in direction of the first vector A. Step number 2, curl those fingers in direction of smallest angle toward the second vector B. Step number 3, thumb, which is perpendicular to the hand, points in direction of C, the resultant vector. Okay, so this is what we call right-hand rule number 2. Okay, so what this means is then if I want to determine the force on this current carrying wire, we have to use this right-hand rule, since we know that the force then, which is C, is equal to I times the length, which is L, crossed by the external magnetic field, which is B. Okay, so this is basically the way that it works. So let's see how this actually works. Let's draw a couple examples and see how this actually works. So let's say I have vector A. So I don't know, let's say vector A points this way. And let's say for funsies, I don't know, vector B points downward. And what I want to know then is what is the direction of C? So what's vector C? Okay. So again, the way this works is we point first our fingers in the direction of A. So in this case, A points in this direction, so I put my fingers in the direction of A. Okay, so A points this way. Then step number 2 is I'm going to curl my fingers towards B in the direction of the smallest angle. Now, since B points downward, then the direction of the smallest angle is to put my palm downward and rotate my fingers then towards B. My thumb, which is at a 90-degree angle to my hand, then points in the direction of the results, which in this case would be this way. So in this case, what this means is that the direction of C would then be into the page. So this is C. Okay. So again, point your fingers in the direction of A, curl towards B, your thumb then points in the direction of C, which in this case would be in this direction. Okay. Let's do another example. Let's now say that A points this way, same direction, but now let's say B, I don't know, points out of the page. So let's take B pointing out of the page. So this is B. What I want to know now is what is the direction of C? So we start off by pointing our fingers in the direction of A. So A is pointing in that direction. B would now be in this direction. So now I curl my fingers in the direction of the smallest angle. So that'd be in that way. So my thumb would then point in the direction of C. So C in this case would be straight up. So C then would point this way. Okay. So let's do another example. Let's do A. So this time I'm going to take A coming out of the page. And let's take B to B. I don't know. Let's go straight down. So this is B. So what's the direction of C? So who could tell me the direction of C? Who wants to be brave?
Would it be pointing to the right?
Good, that's right. So in this case, we know that C has to be pointing this way. Good. So in this case, again, I'd point my fingers in the direction of A. So A is pointing in that direction. So I'd point my fingers this way. B is straight down, so I'd curl my fingers straight down. My thumb then points in the direction of C. So C, as Tara said, would be pointing to the right. Very good. So this is right-hand rule number 2. So right-hand rule number 2 says that the direction of the force is given by this kind of complicated process. But again, the magnitude of the force, let's go back to here, is simply given this way. So the magnitude of the force on the wire is just simply the current times the length times the external magnetic field times sine and angle between the two. And then the direction of that is given by this right-hand rule.
I'm not really understanding.
So, which part? Just how to do it or why?
How to do it.
How to do it, good. So we always have to go back to the structure of what we're looking at. So the structure we're looking at is A cross B is equal to C, okay? Now, as the structure changes, what's gonna happen then is what? The way that we do it is going to change, okay? So the way that this says, again, is that step number 1 is we point our fingers in the direction of this. Step number 2 is that we curl towards this. And step number 3 is our thumb gives direction of this. Okay. So here, so let's go back to that first one. So what this says is that, again, we point our fingers in the direction of the first vector, which would be A. So again, it's pointing in this direction, so I point my fingers this way. Then I want to curl my fingers towards the second vector, which would be B. So to curl it towards B, I have to put my palm down and then curl my fingers towards B. My thumb then gives me the direction of C, where my thumb is, if I can bend my thumb a little bit further, 90 degrees from the rest of my hand. Right? So again, I point my fingers towards A, curl towards B. My thumb then gives the direction of C, which is pointing in this direction, which I'm thinking about pointing at the direction of my screen. So in this case, it would be pointing into the screen. For the middle one down here, again, A would be pointing outward, so that's what we just did. So A would be pointing in this direction, B is straight down, so I curl my fingers towards B. My thumb then goes the direction of C. For the one in the upper right, A points this way, B points outward, so I put my thumb pointing outward, curl in this direction, so C would then point upward. Okay. So it always depends on exactly what this thing looks like. So you always point your fingers in the direction of the first vector, curl them towards the second vector, thumb points then in the direction of the third vector. Is that okay, Miranda? You feel a little bit better or still the same?
Okay, with the first one, so
Sure.
you go to the right,
Uh-huh.
so it's like this.
Yep.
And then you curl down and your thumb is going like this.
That's right.
And I'm confused how that's not to the left.
Well, look what your thumb is doing. Your thumb is pointing towards your computer screen, right?
Okay, so then that's towards the page.
Correct. Exactly.
Okay.
Exactly. So that's what this X here means, is that it would be pointing into the page. Exactly. Exactly. Is that okay?
Maybe.
Good. So why don't you try this one over here? So let's do that one together. So which is the direction of A? So point your thumb, your fingers in the direction of A again. So they're pointing to the right.
Which one are you wanting to do?
This top one here. Let me get my, so this one. Yeah. So your fingers would point to the right.
Fingers to the right.
Good. B is coming towards you. So curl your fingers towards you.
Curl them towards me. And then that's up.
Correct. Good.
Okay.
That's right. That's right. Why don't we try that bottom one too, just to reinforce everything. Good. So which way is A pointing this time? So A is now pointing away from you. So now point at me. Good. B is now downward. So rotate your palm down. Good. And your thumb always points straight out. Good.
Okay.
Very good. That's
okay.
right.
All right. I think I get it.
Okay, good. Very good. Yeah, so this is the right-hand rule. So again, this is how we determine only the direction of the magnetic field, right? Other than that, the magnitude again is given by on the other page. So again, let's write down our force. So here we know that the force then again, so this is the force on the wire. So this is equal to the current times the length. So the length here is equal to A, what we wrote before. Cross then by B, so B is still equal to B, and F now is equal to C. So here, the way we would do it is we would point our fingers in the direction of L, i.e. in the direction of the current, cross them towards B, and then our thumb is going to give the direction of that force. Okay, so that's the way we're going to read this. So good. So, having done all that, let's do an example. So this example says that we have a rectangular loop of wire hangs vertically in an external magnetic field where that external magnetic field is perpendicular to the wire and points towards you at all points. So it's going to be pointing out of the computer screen into our faces. So then it says, and a portion of the wire that is, it's supposed to be an L. Let me write that as a capital L. There we go. Capital L equal to 10 centimeters long. A downward force is determined to have a magnitude of 3.48 times 10 to the minus 2 newtons when the wire is carrying a 0.245 amp current. So it wants to know what is the direction at which the current is running through the wire, and then what is the magnitude of that magnetic field. So let's draw what's happening. So here's going to be my rectangular loop of wire. So here's my rectangular loop of wire. And it tells me that this portion across here has a length L, which is equal to 10 centimeters. Okay. Now it tells me that there's current running through here, but what I care about is the fact that down on this bottom portion, there is a force where that force is pointing downward, and the magnitude of that force is equal to 3.48 times 10 to the minus 2 newtons. 3.48, right? Yeah, good. So from here, the first thing we want to know is what is the direction of the current? So meaning, is the current in this wire running in this direction? Or is it running in this direction? So which direction is this guy running? Then we're told that the magnitude of that current is equal to 0.2 something 45 amps. So from here, it wants to know what is the magnitude of the magnetic field. I just realized I wrote that as F, not B. That should be B. Sorry, I'll change that later. Okay. It's okay? So again, what we want to know is what is the direction of the current? That's the first thing we want to know. And then the second thing is we want to know what is the magnitude of this magnetic field. That'll be the easy part. So first of all, what's the direction of the magnetic field? So again, what we know is that, written as a vector, we know force is equal to the current times the length crossed by the external magnetic field. In this case, what we know is that the direction of the force is downward. So we know this is the direction of F. We know that our magnetic field is pointing out of the board. So our magnetic field looks like this. So this is our B field. This is what we're told in the problem, that this thing is pointing outward in all directions at all locations. So in this case, we know that B is pointing out, and we want to know what is the direction of I to get that to be true. Okay. Now this is a little bit different than the problems we've just been looking at. For those, we know the directions of the first two vectors, and we're looking for the direction of the third. But for this one, we know the direction of the second and the third, and we're looking for the fourth, for the first. Okay. So, getting rather dark outside. Here, let me turn on some light. Probably not going to be much, but that's fine. So in this case, we want to know what direction do we have to point our fingers so that when we curl them going outward, it then points down. Okay, this is what we want to know. So let's try. So let's say initially our current is going in this direction. So if we did in that direction, we point our fingers in the direction of the current, curl towards the external magnetic field, which would be outward, right? So if we put our fingers here, we'd have to rotate our palm this way, curl outward. Our thumb would then point in this direction, which is the direction that the force is, which means that would be correct. So here, our first trial, which says that the current running in this direction. So again, we put our fingers in the direction of the current, curl towards B, our thumb would point in the correct direction. Now, if I did it in the opposite direction, so if I did I was pointing this way, B was this way, my thumb would point upward, which would be the wrong direction, which means that our current can't be running in this direction, it has to be going this way. So here, the first thing we can tell is that our current points to the left. To the left. Good. Now, for the next part, what we know is that the force is equal to the current times the length times the external magnetic field times sine of the angle between the two. Now here, we know is that the current is moving to the left, but the magnetic field is pointing outward. So what is the angle then between the current and the magnetic field? So I have the current going this way, magnetic field is pointing straight out. So what's the angle between those two? What do you think?
Is it 90?
It's 90, good. So in this case, if the current is running, this way, magnetic field is going this way, well, if I simply rotate that like this, that's 90 degrees. Exactly. So in this case, what you can tell then is that what? The angle is equal to 90 degrees. Sine of 90 is simply equal to 1. So we can see that the force then is simply equal to I times L times B times 1, which means B then is equal to F divided by IL. Good. So this then is going to be equal to B, which is equal to the force, which is 3.48 times 10 to the minus 2 newtons, divided by the length, which is 0.1 meters, divided by the current, which is 0.245. Plug in our numbers, we find in this case then is this works out to be 1.42. And the units of a magnetic field are called T. So the units on a magnetic field are T, which is called a Tesla. So this is the SI unit that we're going to use. This is Tesla. Of course, there's other units like Gauss and other things, but we're going to simply use the Tesla. Okay. Before we move on, so let me just point out a couple things about cross products here. Just a couple properties, so something that you should know. So number one, so properties of cross products. Good. So properties of cross products are number one, that the resultant vector, so C, is perpendicular to both A and B simultaneously. Okay. So basically, what does that mean? So that means if I had A was pointing in this direction, B was pointing in this direction, so I put my fingers here, curl down in this direction, so my thumb would be pointing outward. So this would be the direction then of C. C is simultaneously perpendicular to both A and B. Okay. So this is always true. So basically what that means is what? Property number two is that A and B create a plane, and C is perpendicular to that plane. And C is, oh, I wrote B, is perpendicular to that plane. Number three, I was going to write this down, but basically the magnitude of C is equal to the area created by A and B. So what does that mean? So that means if A points this way, B points this way, then if I extend A here, so if A came this way, and then I extend B here, so this is B, then the magnitude of C is actually equal to the area created in this wedge here. So this is the magnitude of C. So the magnitude of C is equal to that area. The most important one of all the ones that we wrote down is actually just this one. So the fact that C has to be perpendicular to both A and B. So when you're trying to determine the direction of that force, if your force is not perpendicular to both A and B, then you know you did something wrong. Okay. So just to point that out. Good. So next thing we want to talk about is, so now we've seen the force on a wire, but remember that current is nothing more than charged particles. So those charged particles are moving, which means that when I deflected this beam over here, I wasn't really deflecting the current, I was deflecting each individual particle. So we can now find the force on a charged particle. So a charged particle moving in an external magnetic field is going to feel a force. So we want to know, what is that force on a charged particle? Well, we're going to start off with exactly that force. So we know that the force in this case then is equal to, let's write it as a magnitude, the current times the length times the magnetic field times sine of the angle between the two. Now, current, we know by definition, is equal to the number of charges divided by the time, right? So this is the change in charge, where I'm writing the change in charge then is equal to the number of charge times the magnitude of the charge. And we also know that for a charged particle which is moving, so this is my charged particle, moving, say, with a velocity of v, then what happens then is what? In a time frame of delta t, this is going to sweep out a line. So if this is time frame of t, this is going to move a distance of L, which means L is going to simply be equal to the velocity times the time. So I'm going to use those two things here. So I'm going to rewrite this then as the number of charges times the charge divided by the time, times then the velocity times the time, times the external magnetic field, times sine and the angle between the two. So here I'm just rewriting the current, here I'm rewriting the length, and the rest of this stuff I'm keeping the same. So this time here is the same as this time, so this portion is going to cancel. So this is going to be equal to then the number of charges times the charge times the velocity times the magnetic field times sine and the angle between the two. So this is the force on a collection of charged particles, which means that the force on a single charged particle is then simply equal to the charge times the velocity times the magnetic field times sine and the angle between the two. Or if I write it as a vector, this is equal to Q times V cross B. So this then is the force on a charged particle. So a charged particle moving then in an external magnetic field is going to feel force, where the magnitude of that force is going to be given by the charge times then the velocity times the magnetic field times sine and angle between the two, which means that what? If it's moving in this direction with a velocity of v, and this is, say, the direction of the external magnetic field, then the angle is the angle specifically between the velocity and the magnetic field. So that is our angle. Again, this is given by the right-hand rule. So what this says then is what? To determine the direction of the force, we would then point our fingers in the direction of the velocity, curl them towards the external magnetic field, and then our thumb would give the direction of the force. So in this example, my velocity points this way. My magnetic field is above that, so I'd have to rotate my palm pointing upward. So I curl my finger towards the magnetic field. My thumb would then point in the direction of the force, which means in this case, the force would be out of the page. Okay. So what this tells me then is that what? Any charged particle which is moving somehow perpendicular to a magnetic field will feel a force. If it moves parallel to the force, it is not going to feel a force, or sorry, if it moves parallel to the magnetic field, it will not feel a force. So if I had my charged particle, say, was sitting here, here's Q, moving in this direction with a velocity of v, in an external magnetic field pointing in exactly the same direction, or anti-parallel to that, the amount of force that this thing feels is simply equal to 0. It will not be deflected. It does not feel a force at all. So for it to feel a force, it has to be somehow perpendicular to the magnetic field, say as in this case, in which it's then going to feel a force, but it'll feel a maximum amount of force when it is perpendicular to that magnetic field. Then we're going to get the greatest amount of deflection due to the greatest amount of force. So that brings us to our next question, which says, we have an electron which is traveling at a velocity of 2 × 10⁷ meters per second in a plane perpendicular to a magnetic field of 0.01 Tesla. Describe the path of the electron. So let's talk about this. So for funsies, let's say the magnetic field is, I don't know, pointing out of the page. So let's say everywhere here, we have a magnetic field which is pointing outward. And we know the magnitude of this field is 0.01 Tesla. Okay. Now we're going to have an electron. So let's say here's my electron, E minus. Let's say moving in this direction initially with a velocity of v. What we want to know then is, what is the path that this electron is going to follow? This is what we want to know. So again, let's write down our force. We know the force is equal to the charge times the velocity crossed by the external magnetic field. Okay. So first of all, let's think about the force and think about what's actually happening. Now, this charge out here, it gives us a little bit of a complication, because remember, the charge can be both positive or negative, which means that what? If we're dealing with a positive charge, in this case, we would point our fingers in the direction of the velocity, which would be this way. curl towards the external magnetic field, which would be outward. So I point my thumb in this direction, which means my force would be upward. But that Q being negative means that I have to take that force and actually rotate it by 180 degrees and point it into the opposite direction. Okay? Because remember, whenever I have a negative charge, that takes that force and rotates it by 180 degrees. Okay? So in this case, what that means then is that this thing is going to feel a force at this point, which is going to point straight down. Okay? So it's going to be the direction of the force, which means this thing is going to feel an acceleration, and that acceleration then will be towards the direction of the force. And again, the reason this is pointing downward and not upward is because of the fact that this is a negative E, right? That negative sign makes sure that it rotates by 180. Rotates by 180 degrees. Okay. So again, if I point my fingers in the direction of V, curl towards B, my thumb should point upward, but because of that negative sign, I get an extra 180 rotation, so now it has to point downward. So there. So here we know the acceleration is towards the center, so let's look at the path. So what would happen then is that this thing is going to start to curl, and it's going to go to some point, let's say here. So at this point, what happens then is that what? The velocity is going to point in this direction. So now let's think about the force. Now look here is that the acceleration is perpendicular to the velocity, which means the magnitude of this velocity is not going to change. The only thing that's happening is it's pointing in a different direction. So in this case, we now point our fingers in the direction of the velocity, which would be down in this direction. We would curl towards magnetic fields, or our thumb would point this way. But again, it's a negative charge, which means we have to rotate. So our thumb points in this direction, which means here, the force now is going to point this way. Okay, so this is the direction of the force, which means the acceleration is now going to point this way. Okay. So this thing is going to continue to curl. So this is going to curl, and now it's going to end up, say, somewhere here. So at this point, we know then is that the velocity is going to be straight downward. This is the direction of the velocity. Again, the magnitude has not changed because the acceleration is still perpendicular to the force. So here we point our finger straight downward, but the magnetic field is away from us, so we'd have to rotate our palm this way. Curl in this direction, our thumb would then point here, but that negative sign means we have to rotate 180 degrees, which means it points towards the center. So it means at this point, our force is going to point this way, which means our acceleration then would point this direction. Right? If we keep this up, what we're going to notice is that the path that this electron is going to follow is actually going to be a circle. So as long as the velocity is perpendicular to this external magnetic field, the electron then is going to curl around in this direction. Right? It's going to curl around in a clockwise direction. Now notice if this was a positive charge, it would just actually curl around in the opposite direction. So if this was a positive charge, it would actually still do a circle. It would just curl around in this direction. So if it was a positive charge, it would curl around this way. But the electron being a negative charge, it's actually curling around in this direction, so the opposite direction. Okay. Which means that this thing is actually undergoing uniform circular motion. So the description of the path is that the electron undergoes uniform circular motion. Which means that this thing is going to sweep out a circle which has a radius of r. So this is our radius. So what I want to know then is, since this thing has a uniform circular motion, meaning that the velocity magnitude stays the same at all points, it just points in different directions, undergoes a circle of constant radius. So we now want to know what is the radius of the circle. So the way we do that is, let's take our charged particle to be here. So in this case, what we know is that the magnitude of the force is equal to mv squared over r, since this is moving in uniform circular motion. The only force acting on this is the force due to the fact it's in an external magnetic field. So this is going to be equal to the charge, which is the fundamental charge, times the velocity times the magnetic field times sine of the angle between the two is then equal to mv squared over r. Now, in this case, the velocity is always in this plane. Let's call this the xy plane, where the magnetic field points in the z direction, which means what is the angle between the magnetic field and the velocity at all points? Go for it, Jolie. It's gonna be 90 again, right? Because again, the velocity is always in the xy plane. Magnetic field is in the z direction, which means the angle is always gonna be 90 degrees. So it's gonna be E times VB is equal to mv squared over r. So this v is the same as this one, so we can cancel that out. So finally we can solve for r. So this tells me that r then is gonna be equal to the mass times the velocity divided by the charge times the external magnetic field. This is an electron, so this is 9.11 times 10 to the minus 31 times the velocity, which was 2 times 10 to the 7th, divided by the charge, which is 1.6, there we go, times 10 to the minus 19, times the external magnetic field, which is 0.01 Tesla. So here we find that the radius of the circle that it creates is 1.1 times 10 to the minus 2 meters. So it's about what? 1.1 centimeters. So in this case, given this velocity in this magnetic field, this circle is going to create is about 1.1 centimeters. Now, other things we know about this is since it's going to be moving in uniform circular motion, that means it's going to have a period. So what's the period? So the period then we know is going to be what? 2 pi times the radius divided by the velocity, right? Okay with that? So let's use that radius from the other page. Sorry, let's go back. So it said that the radius was equal to mv e over b. So let's use that r is equal to mv over eb. We're going to just call that q for now. So this is then going to be equal to what? 2 pi times m times v over v times qb. So the v's are going to cancel. So this is now going to become 2 pi m over qb. Which means the frequency, which is then equal to 1 over the period, is then going to be equal to the charge times the magnetic field divided by 2 pi times the mass. Okay, so this is the frequency, and this guy is the period. So as long as our charged particle is moving perpendicular to the external magnetic field, the path of the particle will be a circle, where the radius of that circle will be given this way, the frequency is given this way, and the time, or the period it takes to complete one circle, will be given by this guy. This frequency here is what's known as the cyclotron frequency. Which basically has to do with the energy which is radiated by the charged particle as it is being accelerated through a circle. So basically, old school particle accelerators were done by what's known as the cyclotron, which basically took a charged particle and actually rotated them in a circle. And as they rotate in a circle, what ends up happening is they give off radiation, i.e. light. So this was actually an old style particle accelerator. So as it actually goes around and it's giving off radiation, this is then the frequency of that particular radiation. Okay. Where we see this a lot in nature is actually the Aurora Borealis. So this is the Aurora Borealis, the northern lights. These beautiful lines that you're seeing, and actually how they're rotating around and all that different stuff, is actually nothing more than the cyclotron radiation. The colors that you're seeing here have to do with the type of particle that it's interacting with in the atmosphere. So basically in the atmosphere, we have both nitrogen and oxygen and all kinds of different stuff. So all of these different colors come from the fact that what's happening is we talked about solar winds before. So solar winds are when the promenades, which come out from the sun, break apart and it sends charged particles towards us. Those charged particles then head towards the Earth and they end up interacting with the Earth's magnetic field. So let's kind of draw what's actually happening here. So here is the Earth. Here's the charged particles coming from the sun. And then this is the Earth's magnetic field. So what ends up happening is these charged particles, let's say I have some coming in this direction, end up getting caught up in the Earth's magnetic field. So we can think about the velocity as part of it is pointing this way. So this is the parallel piece of the velocity. This is then the perpendicular piece of the velocity. The parallel part of the velocity only causes it to keep moving in that direction, because remember, there is no force in that direction. But the perpendicular piece causes that magnetic, or that charged particle, to then wrap around this magnetic field. So basically what happens is this charged particle, which is moving in, gets caught up in the Earth's magnetic field and then starts to spiral around the Earth's magnetic field. Now, what ends up happening though is, oops, sorry, if we go back a page, the closer and closer it starts getting to the pole, well, the strength of the pole, because the density of the field lines is getting bigger, then the frequency gets bigger, the period gets smaller, the radius gets smaller, which means that it starts giving off more and more and more energy. Okay? So as the particle starts getting closer and closer to the pole, the radius of this starts getting smaller, the energy starts getting bigger, so the radiation that it starts sending off in all different directions is getting larger. So what that does is it sends off the radiation. That radiation then interacts with the charged particles, which are in our air, or just whatever particles are in the air. So again, nitrogen, oxygen, etc., causing them to ionize. Once they ionize, that strips off particles, which then gives off light. So this light that you're seeing here is actually from that synchrotron radiation from these charged particles interacting with the natural elements which are in the Earth's atmosphere. So those lines that they're actually following there are actually the Earth's magnetic field. So what it's actually doing is it's mapping out the field lines for the Earth's magnetic field. And all that light is actually just coming from the ionization of all of the particles in the air from nitrogen, oxygen, and again, etc. So what you're seeing here is actually there's a lot of activity coming on from the sun. So you actually see a lot more activity from the northern lights when we have a lot of sunspots. So basically what happens is a sunspot is created by magnetic fields from the sun going out from the surface of the sun and coming back in. So each one of those sunspots corresponds to a beginning and an end of a magnetic field line. So meaning the more sunspots that you have, the more charged particles are being sent from the sun to the Earth. So you get a lot more activity of the northern lights during the time of these, a lot of solar activity, meaning so a lot of different sunspots. So if there's not a lot of sunspots, then there's typically not a lot of activity in the northern lights. But again, that's all the northern lights are. So the northern lights are the synchrotron radiation, which is being given off due to the fact that these charged particles are spiraling around the Earth's magnetic field, and the direction of these paths that you're seeing is actually the direction of the magnetic field itself. So I will stop talking. So I think that's about the end of that. So good. So tomorrow we're going to keep working on this. So we're going to start talking about other things that you see a lot in chemistry, for example. Things like mass spectrometers, as well as the discovery of the electron, all involve these things. So we'll talk about how all that's actually involved, and then we'll move on from there. But this is just the force. So again, the right-hand rule here simply tells you the direction at which that force is being applied. And again, the angle there is the angle specifically between the magnetic field and the velocity. So in most cases, that's going to be 90 degrees, but we'll see times that it's not going to be. But anyway, so any questions, ladies? Looks like the other two were having internet issues, but that's fine. Everybody's doing okay? So far, so good? Yeah. Okay. Well, in that case, have a good night. I will see you tomorrow.